Mm-hmm. Normally not at all, because the compiler, when creating a release code, will be smart enough to do all the optimizations that are reasonable automatically. So it's mostly important if you would want to somehow manipulate how an existing program works, or understand how a program where you don't have the source codes to is operating. Mm-hmm. Mm-hmm. Yes, and the question? Um, so one reason to do it, if you have some loop that will use the loop iterator to do arithmetical operations with pointers, then it is good practice to use size t also as the loop iterator, because then all the operations will use the same size variables. If you would use some pointer arithmetics and use an integer, then in certain scenarios you might maneuver yourself into a situation where you get a value overflow, so that the value in some intermediate computation step will no longer fit into the variable the compiler chose for the intermediate value, and then the result will be invalid. So if you use a variable where you know that it is large enough, then you're on the safe side that such thing cannot happen. Any more questions? Mm-hmm. Mm-hmm. That would be some assembler reference for the x86 CPU, for example. So that quickly gets quite complicated. I haven't seen any good resources like on the intermediate level. Usually it's either full-on assembler programming, or just C without telling what's happening underneath. So what you can take a look on is just a opcode list for x86, for example. Let's see if I can find a link quickly. Yeah, this one is good. So this site, once it loads, provides a list of all the different opcodes and opcode variations that are there. Where's the internal chat here? Suck. And there should be also a 64-bit version of that somewhere. Yeah, and that's the 64-bit version, which is mostly identical. It's just so when they introduce the 64-bit extension, it's really just they try to have as little changes to the old 32-bit scheme as possible. So they basically used mostly all the same opcodes, just added additional extensions such that you can use them for 64-bit. And when you scroll through the list, then you see all the names of the opcodes and a short description what they are doing. And if you want to know more details, then I would just recommend googling one of those opcodes. Other than that, as said, just some book that explains assembler programming would be also a good resource. But as said, that would be rather very complicated very quickly. Any more questions? Okay, so if there are no more questions, then let's start. So the last time we taken a look on function calls and how they are implemented. I think, if I remember correctly, one thing we have not yet taken a look in more detail was how the different function call, what's the English word for that, conventions operate. So one thing to keep in mind is, of course, that for 64-bit there pretty much is just one calling convention and that's it. But what we could take a look at here quickly would be how those calling conventions look for 32-bit, and take a look through the different calling conventions that we have at our disposal. So maybe let's quickly, for reminder, start with the 64-bit one. Jump to our function 10 and run it and see the debugger. So we have a function to which we are passing 10 arguments, and these are all integer arguments. So the first 4 of the arguments on 64-bit Intel, or rather 64-bit AMD architecture, will be passed through registers. So you see here ECX, EDX, as well as R8 and R9 are used, and the rest of the arguments have to be put on the stack. And one thing to keep in mind when doing function calls on the x64 platform is that you are supposed to have reserved enough room on the stack such that the function could put those arguments into one consecutive memory area with the other arguments if the function so chooses, and only then the call function will put the return address. So when we put a breakpoint here and go one step in, then you see here that the first thing the function does, so it takes the stack pointer and it adds to it the 4 register values, the 4 arguments that are passed on registers. This is not necessary. The function is free to do it or not. The function could reuse this area of memory for some other computation, and under the assumption that the function will usually need some intermediate variables, there is a good chance that this memory will always be used, so allocating it in most cases will not be wasteful. And if this is enough room, then the function does not need any own memory allocation, so this saves at least 1 or 2, well, 2 operations. In debug builds, usually it will always just reuse this area to save those registers. And the reason why it starts with the return, the stack pointer +8, and then continues is that once, when we go back to where we were called from, that once the call opcode is executed, an additional entry is added to the stack which points to the return address. So if we would want to take a look on the stack how it looks at this point, we would have our 1. We started 1, yeah. So until here we would have then stack, then we would have 4 empty spaces, and then as soon as we do the call, so once we arrived here, at this position would be the return address. And then those 4 values will be filled by the function with 3, 2, 1 with the other addresses. And now we can, for example, put a breakpoint here, go to here, and then let's take the stack pointer with the intermediate window +8. We say that this is an int asterisk, and as you see we get the first address. And if we can of course also say that it's a int64. In this case you see that there is some memory just contains garbage data, because this here operates in increments of 8, and our data might be less than that. And since the function knows its own argument types, it here uses the double word instead of quad word. Whether that actually saves anything, I don't know. I don't think so, because the CPU should be able to execute a quad and a double word move in the same amount of time. It might save some femtowatts of energy perhaps if it does not copy some other switches, but that's the important thing to know simply is that the data might contain some garbage when you would try to convert this into an array. But the nice thing about this array is that we can address it. We need to put this in one more brackets. And then just use some loop to step through all the arguments. 3, 4, 5, 6, 7, 8, 9, 10. Sorry, 9 was already. 9 was already it. And as said, the way the memory is aligned is a bit wasteful, since as you see here, half of the memory is pretty much just filled with garbage and not used. But the advantage is that you can construct these variable argument functions like this one, which we have already taken a look I think last time, where you can pass an arbitrary amount of arguments, and stepping through all those arguments becomes very easy, since you just are basically are getting one array through which you just need to step in increments of 8. Now let's first take a look on the other calling conventions in 32-bit mode, and then we will take a look on how this changes when we use different data types. Since as far as I remember, last time I only mentioned that quickly since we were running out of time, so that was not in the full detail that one might potentially want. This to here. So as you see here, the typical 32-bit calling convention will use push operations to put all the arguments on the stack, so no registers are used at all. And then once we are done here, all the entries will be removed from the stack at once. And also, of course, here the stack will be filled with 32-bit numbers. So when we enter into our function, we see it's much simpler, because it just has to do whatever it would want to do internally, although it does a lot of in our case unnecessary things, since it's not unoptimized debug code. So it saves a register, then it updates the register here in those two operations. So first of all, it saves the old EBP, it saves the current stack pointer, so where the stack for the function would begin, into EBP. Then it allocates some memory on the stack for the functions, which it will not use, but it does it for really no good reason. So it's just some way how the compiler by default implements it. If we would run this as a release build, it would not do those operations which usually are not needed. It would just optimize everything away that does not fulfill a function. Of course, if we would have more logic in the function, then we would need this memory. Okay, next thing, it saves 3 registers to the stack again, which it does not need since it doesn't alter them. Then it uses the XOR operation to just set EX, so the return value register, to 0, and then it just undoes everything it did. So it pops the 3 values from the stack, it restores the original stack pointer from the EBP register, and then it restores the original EBP register and returns from the function. And when we return, then the caller will clean up the allocated stack using this add operation to the stack register. As you may remember, the stack in 32-bit starts with a E, not with a R, the register name, to indicate that it's 32 and not 64-bit operation. And then the last thing it does here is it just moves the AX register into memory where we want the return value to reside. Okay. Now when we switch the calling convention, we can use these keywords here. So std call, ccall, fastcall, and vector call. And for example, most of the Windows API is using this std call convention, which is a bit, it has a small optimization. When you look here, the passing of arguments looks identical, but you can see that here the add ESP, what was the number, 28 or something, is missing. So the function that calls something is here no longer responsible for cleaning up after the call. So when we enter our call 10 function, we see that it looks pretty much the same. It does a lot of nothing. It returns 0, and then here the return operation is different. Instead of just red, it says red and the number. And we can display code bytes. Yep. So normal red would be, what was it, C3 I think, and the red with a number is C2, and then it takes 2 additional bytes of information, which is the amount of stack space to release. And as you see, it can go up to a 16-bit number, so we could release up to 64K of stack space, which is a lot. Usually you would not have this many arguments anyways. And the reason for this convention is that when they were designing, I guess, Windows for the first time, I don't really know the historic reason behind it, but it's a reasonable assumption. They had systems which only had a couple tens of megabytes of memory, so any byte you could save in your applications was worth saving. And this way, while the function that you want to call is slightly larger, every single call then already saves you a couple bytes of memory. So we can quickly switch back to the... So the normal calling convention would be the C call, this one. So when we now run the code, we will see it looking like during the first go through in the 32-bit version. And here you see it takes 3 characters for this add operation. So if you have a function that calls, so if you have 300 function calls somewhere, then you would already save 900 bytes of memory, which is not nothing on a, let's say, 8 megabyte system. Of course, nowadays this is not longer a concern in this to this extent. So the modern calling convention just lets the function which calls clean up the stack. And also there are quite a few optimizations that can be done. So when you are calling a function, and then you don't in principle need to allocate stack and then free the stack and then allocate stack and then free the stack. You can also just allocate the maximum stack you would ever need within the function call at the beginning, and then just reuse certain areas of the stack as you go along inside your function. This of course is, from a perspective of assembler code, highly confusing, because you are pretty much reusing. It's like you would call a variable, let's say variable 1, and then it's in the middle of your use completely change its meaning and then use it for something else. And of course you need to track whether the compiler needs to track whether when it was reused, and then don't try to do something with it assuming that it is something it is no longer is. That wasn't correct English. Sorry about that. But you get the point. And of course, if you would be writing assembler code by hand, then you would either write code that uses more memory, or you would have a very hard time to write everything correctly. But since nowadays normally you only write extremely small code portions in assembler, if at all, and the rest is done by the compiler, compilers can very efficiently track all the memory area and register usage, and then reuse everything to get the smallest memory footprint and the highest execution efficiency. Of course, there always is a certain trade-off. So as mentioned, there is a setting where you can set, do you want rather a smaller file or rather a faster executable. So this trade-off can even be communicated to the compiler such that it will do whatever you need most. And then so yeah, what I wanted to say is the 64-bit calling convention might look a bit more wasteful, but in practice it will not be that much wasteful. The most wasteful thing about it will be that it uses memory in blocks of 8 bytes, and if you only have integer values, then a good portion of that will simply be unused. But I guess at some point rather waste some memory than make things too complicated. So to finish this part of the calling convention, we have 2 more calls, fast call and vector call. They are both somewhat similar, and as mentioned, they only have a meaning in the 32-bit version of a program. So here you see that the fast call somehow looks like the call in 64-bit. So it's not quite the same. You are still using push instructions instead of moves, and you don't need to allocate any special space for the function, but you are passing at least 2 arguments as registers. And then of course when we go into our function, need to click twice more. The function here, it will use the registers. Well, it would use it if we would use it, but it looks differently. So here it already prepares the base pointer and reserves some space on the stack, saves some registers it does not use, and then here it will put those 2 registers on its own memory, but they will not end up in a consecutive memory area with the other arguments which have been passed to it. So if you write a variable argument function like this one, the compiler will always default to using the ccall formatting instead of, and will ignore, if you would have a fast call prefix, it would just ignore that. The idea here was that if we would have the optimizations on and not be wasting time doing meaningless things, then if it would be a very simple function, it could just directly take the registers, do some operation, and then return the result. So we could actually try to take a look how that would look. Let's say that we want arg1, we want to return the sum of argument 1 and argument 2. So let's put a breakpoint here. Sorry, I want to put this here with this one. We run the code. Now since it's still a debug build, it will not be very efficient. It just saves the registers to memory and then takes it from memory and then does the operation, which is kind of pointless. But if we switch now to release build and run it, it should create a much shorter code, which should in fact highlight the performance advantages of using a fast call. It didn't do anything. Okay, the code if this, apparently the optimizer is too smart. It decided, since the function return value is ignored, then let's just not do anything. It completely optimized the way our function, but let's, okay, that also didn't work. Or is there something broken? Does not create any debug information or something like that. Let's see. All options. Okay, it generates debug informations, and here linker. It should be generating debug informations. Get char should be defined. Why is that not? That should be in stdio. It's not. Was it get char? Which header do I need for that? Get functions, yeah, and we need the header stdio. That we have. Why would that not work? Get char. Okay, now this works. Okay, so at least we do something, but as you see, it didn't do anything with pretty much anything. So let's let's use the input and the output, and maybe, yeah. Okay, now it must do something because it cannot predict what the whole thing will be doing. So let's put a breakpoint here. We probably reused it already, so let's use my red X. Okay. Okay, and as we see now, it did not kill the well. It still killed the function. It just did what the function would do internally outside here without doing even a function call. That will be our options. Inline function expression disabled, and let's get two values such that the thing will not be able to make too many assumptions about what it will get. Okay, so this worked out, so we have our function call, but I think we need to disable some more things. So if you have actual production code, and the release code, the release build code is of course much more helpful. But if you have like synthetic code which doesn't do anything, then oops. I wanted to change that. This one we want to disable. Okay, let's see if this will yield a clean enough code. No, it still uses something. There's like a second function call for some check that the thing adds general support all options. Let's go for this. This is not. Let's do that one. We don't want this either. Security checks also disabled. Security checks. Okay. Let's see if we get. Okay. Well. Okay. Then let's just ignore that. Here we have our function call, and when we enter it, as you see, the whole function only is made out of two instructions, and it uses the layer instruction to make an addition of two registers. So this is something you will see a lot when reviewing x86 assembler, that often instructions are reused in a way which is not necessarily what the documentation says they are for, but the result works, so it's being done. And in this case, the load effective address instruction is used to make an addition of two registers and save the result into a third register. So the normal add instruction reuses one register, so you would need to copy, for example, in this case, ECX to ARX, and then make add ARX EDX, so that's already two operations. While here, using the layer instruction, you just needed one to make this operation. And then of course we have the return from our function. So this much to release optimized code. We should not we should not look into this too much, because I said it it is difficult to generate good test cases because a lot of things gets optimized out. So let's finally review the last calling convention, the vector call, and as you see here, it looks quite similar. It also uses here 2 registers, so it's not a big difference in this case. Where it would make a difference would be if you would use different argument types. And internally, of course, it would look just like a vector call. So having said that, we can switch back to our 64-bit and did we take a look on this? Yes. And I think that will be this 2 function calls. I think, if I remember correctly, last time we already have taken a look on how function calls look with different argument types. So then it follows the same calling convention. It just substitutes a R or an E register with a MMX or a or another special purpose register if needed. Did we have return by value? We had return by value. Yeah. Okay. So let's save this and continue with the next part of the lecture, which will be memory management. So until now, what we did was we just used the stack to reserve some memory and then release it. Call this project memory. But of course, in more complex programs, you would like to have some memory which might be independent from the stack. So all the memory that is on the stack within the function call tree, you cannot return outside of the call tree. So you can of course use it to pass it down to a function which then will return. But if you would want to allocate some memory within a function and then return this memory to a function which called that function, you could not do that with the stack. So this is of course a significant limitation. Plus there are other limitations, like the total size of the stack is limited to a couple megabytes on modern Windows, and on other systems it might be even more limited. So what you need when creating more complex programs is some method of allocating memory independently from the stack. And in C you can use the malloc function for that. So let's say void imem1. So we allocate new memory, use the malloc function, and then you just specify how much memory you want. So let's go with 1000 bytes, and this function will internally allocate for you the amount of memory. So let's quickly run this, but it is of course a boring test. But let's just see that it really does what we want. So we got a register, and if we want to go to memory, what was it? Debug Windows memory 1. I thought I had that. It's here. Then we see that we have a nice large memory area which is filled with a dummy value, so CD in this case. And if we would run it, of course, in release build, it would not prefill it with anything, but we can now, for example, use memset to clear it. So 0 and then the size. And then if we of course run, it will still work without any issues. So now you see it's full of zeros, and if we keep scrolling, at some point it's no longer full of zeros. There are some data here which we haven't put there, and there are a bunch more zeros after it. And the way malloc works internally is of course dependent on your C runtime. So this is a function which is provided by the compiler C++ runtime. So on Windows it's the one from Microsoft. MSVC on Linux you will use something from the CLib. And of course, if you have some other compiler, it might either use one of the existing C runtimes, or it might bring its own. And at least on Windows, the function will have an internal memory manager. So not every call to malloc will make the program ask the operating system for a new memory block. But of course, the first call, if malloc wasn't used before in the program and at any point, will of course definitely make it as the first thing it does, ask the operating system to give it some larger chunk of memory using the virtual alloc function. And then once it gets this larger chunk of memory, it will start managing this memory. So when you request a small block, it will give you that small block. If you request another small block, it will have memorized which blocks it already gave you and will give you a new one, and then again a new one. And if it runs out of empty blocks, it will ask the operating system to give it another larger chunk of memory. The granularity this operation is performed is well up to the framework and whether they add some optimizations or not. One thing to definitely that you can definitely assume is that the smallest granularity this could work at is the 1 page size, so about 1 kilobyte. And 4 kilobytes is I think the typical page size on Windows. So that I don't know whether I already told you what pages are. I might have mentioned that in one of the earlier lectures, but normally on modern Windows, or for that matter on any modern operating system, the memory which is physically installed in the computer, it has some physical address, but the memory address as used by an application, and pretty much also the largest part of the operating system kernel, except only very few exceptions, will be so-called virtual memory. So there is a part of the CPU's functionality called the MMU, Memory Management Unit, and what it enables you to do is it enables you to, for the duration of the execution of some piece of code, define your own memory address space. So every application that runs on Windows has its own memory address space, and different applications can internally have the same and use the same address, but the address physically will map to different regions of physical memory. And this mapping can be done only with a certain granularity. And on Windows, this granularity is 4 kilobytes, and this granularity is called the page size. So you can specify that one memory page or a couple memory pages will reside in your memory address at a given address, and physically they will be mapped to some location in the physical RAM of the computer. There are of course other architectures. I think the Apple M1 is using a larger page size, I think like 16K or something like that. I can quickly Google that. M1 I know that was one of the the Apple M1 uses 16 kilobyte page size, so it's a bit difficult to run typical, so to port an operating system which was made to operate just with a 4K page size to that. So I think the makers of the Asahi Linux had quite a fun time to getting that to properly work, but of course it's doable. And I think, as far as I remember, with the x86 architecture, you can in fact specify the page size that you want to use. So you could use different ones. So you can use up to 2 megabytes of page size on x86. So it is of course not like an arbitrarily fine granularity, but I guess you can just go in orders of in multiples of 2 from 4 kilobytes, which is the smallest size, up to 2 megabytes. And apparently there is a extension that even would allow you for 1 gigabyte page size, but that is probably not used very commonly since that would be a bit unflexible. The usage of this paging system of memory pages has a couple advantages. First of all, it allows you to give to every application its own memory address space. And secondly, not all of the memory addresses which a program would want to use need to actually reside in the physical memory. So if your computer is running low on RAM, the operating system can see, okay, this and that memory used by those applications hasn't been accessed recently, so let's just save this to disk, set a flag in the page table indicating that the memory is no longer physically present on the system. And then when your application would decide to try to access this memory, this will cause an exception, a page fault, which is then just captured by the operating system, and the operating system will then find some spare memory somewhere on the physical memory, load the memory content from disk back to this memory area, and then update the address pointer in the page tables. So at this point you can change which physical addresses your program addresses using the same internal virtual address. And this is something that I think it was quite a big advantage in the old days, where you only had systems with, again, a couple megabytes of memory, that you could have this virtual memory and greatly extend the usability of your system. Because before that, with memory it was like this: if you run out of memory, then you cannot run the program. Even if you are just a few bytes over, it will not work if it doesn't fit into the physical RAM. But using virtual memory and paging, if it just a small amount of memory doesn't fit, it can be, when it's not in use right now, paged out. And of course, if you would page out a lot of memory of the program, and the program would want to access it all the time, then your CPU would spend most of its time by paging parts of the memory in and out and in and out, and so on and so on. So this makes everything slow, but it still makes it work, in contrary to just something not loading if there is not enough memory. So this is one advantage of pages and virtual memory. But the second advantage is that since all the addresses are virtual, first of all, an application will only have access to its own memory, or memory that was shared with it explicitly, and it will not be able to access memory of other applications. So this gives you quite a large resilience against programming errors, because on older systems like DOS, where you didn't have memory protection, you could just crash the whole operating system or crash another application just by writing to the wrong memory address. On Windows this is not possible, or on Linux, or on any modern operating system, because of this virtual memory system. The program can only access the memory it was assigned, and even this can be further restricted. First of all, you can set memory ranges as read-only, such that the application can read them, but it cannot write to them. And with additional extensions to the paging to the page table system, it was sometime 2000, I don't remember, 2004 maybe, they introduced the NX bit, so an additional flag for the page tables. When was that? 2004, yes. Which can mark memory as non-executable. So before that, any memory in your system which you could access from your program for reading, at least, then this memory you could also just jump to it and execute it as if it would be code. Whether that would make sense is, of course, would depend on whether there is code there or not. But that was in fact one of the mechanisms through which a lot of security exploits were implemented. So you just trick the program into overwriting some portion of its executable memory, or trick the program to jump to some data memory, that some memory containing data you provided, and then you could take over the execution flow, the control flow of the application, and then it was doing whatever you wanted it to do. And with the NX bit, most of such exploits have been mitigated, because ideally memory in any modern application should be configured either as executable or as writable, but never both at the same time. So this way, if the mechanism is used, if you try to bring the program to overwrite some memory which contains program code which could be executed, it will cause a access denied because the write operation will fail on a read-only memory. Or if you try to execute some memory address which contains data, the execution will also fail, because the code area is not marked as executable. Now, whether all applications that are out there are using this mechanism is a different story, because there are use cases where you want to generate code dynamically. So, for example, Google Chrome, its V8 engine, which executes JavaScript code, does that by generating in real time x86 or whatever your platform is machine code from the JavaScript code and executing it. but ideally, of course, the method is your script compiler compiles into some memory area which is writable but not executable, and then when it's sure it done everything correctly, it then switches to read only and instead executable. So it's not like Chrome would not be secure. Quite the contrary, they are using a lot of very modern techniques to improve the security of their execution environment. But other applications might also want to generate code dynamically, and they might not necessarily follow the best practices. An example where you would want to generate code dynamically is if you want, for example, to change the execution flow of an existing library or program. You could try to, for example, to overwrite a portion of a function with your own code that would then detour it to some other code region, and then back. So for this you would normally need to dynamically generate some code. It would not be enough to just load and change some addresses. If you are interested in such things, we can maybe take a look in one of the follow-up lectures how this would be actually done in practice. This is quite an interesting topic, but also quite complicated, so depends on your preferences. But well, that much to this paging system. I think I have mentioned most of the important things here. Yeah, and of course, if we continue in our example, we have allocated the memory now a couple of times. One thing that we should do usually if we want to write proper code is to actually check whether this malloc call succeeded, because it actually is not guaranteed to succeed. It can also return null, indicating that it could not allocate more memory, which could happen if you turn off virtual memory on your system, which you might do because you want the best performance and no paging at all, and then run something that will exhaust however many hundreds of gigabytes of RAM you might have. Then this thing would also run into an error where it could not give you a memory. And there is also a second scenario where you might actually have enough memory, but you might still get an error from the allocating function, and that is if the memory address space is highly fragmented. So if you would request, let's say, a gigabyte of memory at once, then what you need, of course, to get this 1 gigabyte of memory is a consecutive empty memory address area. On 64-bit systems, again, this is a non-issue. Your memory address is go to like 64 exabyte or something like that. So you will never, well, never say never, but with the hardware that is here and that you can envision in the foreseeable future, you will not have 64 exabyte of RAM. So it will not happen that you will run out of empty address space. But on a 32-bit in a 32-bit application, which you might still for whatever reason compile or run, a very common use case would be you got some hardware for your lab, something older, which comes with some libraries which are only 32-bit. Then what else can you do? You need to write your application, at least a small wrapper for the thing, in 32-bit code. So then you have to write 32-bit code, and then you will run into the memory address limitation of 32-bit, which is for the entire address range exactly 4 gigabyte. And because of internal ways how Windows manages memory, this again gets halved. So in a normally configured 32-bit Windows operating system, you would only get 2 gigabytes of usable memory for your applications, and the other 2 gigabytes would be reserved for operating system kernel stuff. So for example, if you would want to share memory between two applications, you would need to ensure somehow that you can get a memory address which none of them have used, and which would be the same for both of them. So in such a scenario, the appropriate operating system function would have used some of its kernel address space and give you an address from this range, such that then both applications can refer to the same exact address, and that you don't need to worry that it might have been already used by something else. So your practical limitation, as mentioned, for the normal use case is 2 gigabytes, and then if you would request 1 gigabyte of consecutive memory, it is quite likely that with just a few allocations you might have already spread your data around the memory space such that there is no consecutive 1 gigabyte area, and in this case malloc would also fail. So one thing to do, which is good practice, is always to check whether it was successful. So if this is 0, then return, for example, or return -1 to indicate an error. And of course, the next thing that you will need to do with your memory is, once you're done using it, it would be good to tell the operating system, or at least tell your memory allocator, that you don't need it, such that it could allocate it to something else that requests it. And you can do this using the free command. So you just write free, and then you provide the address you want to free. And we should do it for the other ones as well, 2 and 3. And after you have freed the memory, it is likely that the memory still will be mapped to your process, because as mentioned, the internal implementation of malloc, which will try to be efficient about what it's doing and how it's operating. And being efficient means, for example, to minimize the amount of interactions with the operating system that you have, since those are those require context switches and are computationally expensive in comparison to just normal local function calls. So if you just release a small amount of memory in your program, you might not see this memory being released on a operating system level, because the internals of your memory allocator will keep on to the memory in case you want some memory later. Then they can give you that memory again without asking the operating system. So this leads to a couple of peculiarities. First of all, this memory area will stay valid, and second of all, if you are not using a debug build, the memory area will in fact keep containing the old data that it contained before it was freed. So we can here take a look in the debug mode. So we filled the memory with zeros, and if we now do free, then you see that it actually changed the content to D, and D is like an indication, a pattern that is easy to recognize, and it tells you this memory has been deleted. And of course, if you then would try to do something with the memory, it is very likely that you would experience a crash, because DDD usually will not be valid in whatever context of whatever you want to do you are doing right now. So this helps you avoid bugs. It is one of the other mechanisms of the debug heap, like that every memory which you haven't touched yet but have requested from malloc is filled with CD instead of DD. So CD means not yet initialized, and DD means deleted. But this is not done by the release heap. So if we try to switch to a release build, unless it again removes all we did here, let's see how well it optimizes things out. Okay, it's not so annoying if you use something non-trivial, but first thing we might see is that C1 will probably not. Yeah, so this one just contains garbage. So this memory we got here is actually filled with some garbage here. It's not even initialized with zeros. It just contains whatever last was there. And well, of course, our memory M1, which we cleared, it will be clear. But once we free it, okay, we see here that there was some garbage put at the beginning, but it wasn't filled or invalidated. So if you would have some text there, most of the text or some data, most of the data would be still there, and this makes programming mistakes of the type use after free quite hard to spot, because if you are not using the debug heap, then most of the data will still be fine, and so most of the application which then would, because of a bug of a programming mistake, try to use this memory with whatever was in it last time, might work to some extent and only crash at some much later point. So such a bug is very hard to trace, and this is why it is advisable to try to be very careful with memory and what you are using your memory for. Okay, so this much to this. So let's now try to use our knowledge to do something that is a slightly bit more complicated. So we can, for example, define a structure of some sort, and what we could do is we can now compare allocating the structure on the stack with allocating it on the heap. Or let's move this further down since we have already this. So what we already know how to do is to allocate it on the stack. So there's my structure, my struct on the stack. Oops, I should not have. Yeah, and if we want to allocate it on the heap, then we need to use a pointer, of course. My structure on the heap, and then this is new. Sorry, and then this is we need casting operator because malloc just returns void 0, void asterisk, and then see off. We need to tell it what size we want. So let's go with this, and voila, we have our first useful structure allocated on the heap. And if you are wondering why the stack is called the stack and the heap is called the heap, with a stack the idea is that you can like put things on it or remove it in the same order you put it on, while a heap is you just throw things at it or pull things out from the middle. It's it's how they came up with the names. Probably one could have thought of something better, but well, yeah. And of course, at some point we'll need to free this. So let's not forget doing that. It's always good practice to write your free function before and then write some code in between so that you don't forget to free. And of course, another thing not to forget is that if you would write here return 0, oops, return 0, then you would never call free. So if you want to return from your function and you have some allocated memory, then you will need to add some additional program logic to ensure that all the memory will be in fact freed properly. So for example, one method of doing it would be to use the goto command that we have seen earlier when we looked at a program flow. Finish, let's call it finish, and then just put all your memory deallocation there. But using a goto, as we already also mentioned, has some limitations, namely that you need all your variables to be defined before you start using goto. So you would need to have some place at the top where we define all the things that we need, and then from here on we can start with our dynamic program code. Let's call it goto finish. And of course, one more thing to keep in mind, we don't want to free something that is not yet initialized, so we need initialize all our variables which might be freed later with null, so that they will only get a non-null value if they are actually allocated. And then of course we use some ifs to ensure that we'll only free the things that have been in fact allocated. Okay, so that much to just a malloc function. At this level we are just looking on things as they are done using normal C. If we are using C++, we get something more, namely the new operator. So let's allocate a second variable. It's fine. It's fine. This equals new, and then we just write the name of our structure, and this will allocate us the amount of memory. But this sort of allocation is not freed with free, but freed with delete. And once we continue to classes and objects, we'll actually see that new and delete are doing much more than just allocating memory and freeing it. But that will be a story for later. Okay, so this much to that. Of course, another thing to keep in mind is that if you do something like this, at this point you will be allocating new memory, and the old memory will stay allocated, and it will not be freed anymore. So you would need, of course, to first by hand free the old memory, and then allocate new one. Oops. If you forget this, then you will never free this memory, and at some point your program will run out of memory. So this is also a very common programming mistake, and actually quite hard to catch when using C or C++, that you just are allocating somewhere objects and not freeing them anywhere. And if you're allocating like hundreds of megabytes, then you will quickly run into a out of memory exception, and you will have a good incentive to find and fix it. But if you are leaking just a couple kilobytes every few minutes, then it may be something that your program will run for a few days before it crashes, and it will be quite difficult to pinpoint where you are not where you are forgetting to free some memory, because as I said, it can be such a mistake, like not just forgetting to use a free at the end, but like reallocating some memory without freeing it before. So there is a lot of opportunity to get a memory leak somewhere in your application. One thing that you can in fact use to some extent to mitigate such memory leaks is to delegate the problem to someone else. On Windows, you can in fact have more than one heap. So by default, when your application starts, it will have one stack per thread and one global heap. But you can create additional heaps. So for example, let's do that quickly. Then my log. I think we need to include Windows H for that. Heap alloc, zack. Yep. So what do we do? Sorry. First we need to create it. Handle heap create. Let's not pass any arguments to it. So we are at this point creating a new heap. Then we can use heap alloc instead of malloc. Then we can even tell it to do the memset for us, so that we don't need to free it manually, and then we can specify the size like with malloc. And then we can of course at some point use heap free. So at this point it's not yet better than what it was. We need to tell it which heap the memory belongs to, and then of course some flags, we don't care, we can just add 0, and the memory block, oops, it didn't have 0, and then the memory blocks are also like 3. But what we can do instead is we can also just kill the whole heap in one go. Heap destroy, and then all the memory, so if we allocated arbitrarily much memory, all of it will be freed once we destroy the whole heap. So that is a valid strategy to just create a heap, pass it along in your functions, may do the allocation if you want to, and then just destroy the whole heap in one go. So of course at this point everything that was on the heap will no longer be accessible. So you cannot allocate something in a function on a custom heap and then return it past the destruction of that heap. Which brings us to the next thing, where to create some examples where such things might be useful. So if you, for example, would have a function, let's call it, let's make a function that returns us something, let's say a string, my test, and let's say we want a function, or let's call it, let's say we want a function that just combines two strings into one, which will bring us to the next subject in our lecture. Const char stern str1 and then str2. Zack. Did we talk about strings? We did not. Okay, we should first talk about strings before we make the example. So let's do some other example before that. Let's say we want to join two arrays. And we need a length for that. Int len1 and len2. So we have two arrays of, we pass the two lengths to our function. What we do in the function will what the function will do, we'll take a look at shortly. Let's do it here. So let's say we want to join mem1 and mem2. So let's fill it up for int x is equals null till 10 x 10 mem1. So let's say this, okay, we need a type for that. Let's say that's an int. There's also an int, and if we have a type, then we need to specify type here as well. Why is it complaining? Okay, and you see already the goto is complaining that we have not allocated this block 1 until something at the top before it. So the goto option needs a lot of discipline to always predefine all the variables at the right moment in time. So let's get just rid of that and that for now. Just move this up here. Block and heap. We also forgot to add this to the deallocation, so that's another opportunity for a mistake. Right here. But going back to this, so we can initialize this with let's say x, and let's do it for both. 2 and 3 are the same, will be initialized with plus 10. Something like that. We just need some data. Okay, so we have our function. We specify mem1 as 1, that the count is 10. Then the same thing with mem3. Mem3, and let's reuse mem1. Okay, mem1 is also a void, so we need to change this to int. Int mem1, and here mem1 is equals this thing. So of course we could have a function where it takes m1 as an argument and the maximum size, and then it will join the two arrays, copy them onto the memory provided. But we want a function which can operate with any amount of memory, and we don't need to specify a buffer for it from the beginning. So here we just create a int stern return ist gleich block int, and since we know the size, we can allocate just exactly as much memory as we need. And now we can use memcopy 1 comma then 1 times caesar of int, then the same an asterisk is missing here, oops, and then red2 and red2, but we need red2 plus len1. That should be fine. So we take the address at red2, we copy array1 onto it. We need to specify the length in bytes, so we take the count and multiply it by the size of one array element. Then here we add the amount of the address, so we do pointer arithmetics using the length of the first array. And this pointer arithmetics, as described already 1 or 2 lectures ago, the plus does not work in increments of 1, but actually in increments of the size of whatever type ret was defined as. So this will be effectively like plus len1 times size of int in terms of the numerical increment to the return value, which will be passed to memcopy, on which it will then just copy the second array, and then we can just return the array. And for example, a use case where we don't, I mean, as I said, this is a very simple use case. We could have, knowing how much, how large the return value will be, just passed a memory block which we have allocated to the function. But imagine a function which would be return, so take one array as input and return a new array which only contains the entries from the first array which are greater than 5. And the idea is that we don't know how many they are. The function is supposed to do that, so the function will in real time need to estimate how much memory it will need. So that, of course, two approaches to that. One is that it will just allocate the whole size and then just use half of it, and that's it, and then just return it. Another approach would be it will allocate the maximal expected size, then start filling it up, and when it's done, then say, okay, how much did I use? Okay, then allocate new block of memory, and then copy in one go only the amount that it actually allocated, which it needs, and then release the memory allocated before that. And what you can also do, in fact, that we can maybe should take a look. There is one more function that you can use. It's called realloc, which allows you to change the amount of memory allocated for a given pointer, but under certain conditions. So if you want to use it to basically release some of the memory, then it should always work, because then it will just write down wherever, okay, we didn't use the whole thing, we now half of this is free, so this is again some free block. But if you want a bigger amount of memory, so a bigger consecutive address range than what was there, the allocator will of course see, okay, do we have enough free memory after the block that I just gave out before? And if then it just extends the memory, and it returns the same pointer it received. But it may say, okay, nope, that will not fit here. Then it finds a new memory block, copies the data over, and then returns a new pointer. So when you use realloc, you must always keep in mind that it might invalidate the previous pointer. So just to make a small example here, mem2 is like realloc takes the first pointer, of course, as argument, so that it knows which memory you want to reallocate, and then let's say 2000. And in this particular case, it's very likely that it will return the same address as it received, but it is free to change it. So after you did realloc, you must ensure that you will always use only the new address and no longer the old address. And the nice thing about realloc is that as long as it can reallocate memory without copying it, it will do it. So it will be much more efficient than if you would allocate a new block, copy the whole thing over, and then deallocate the previous memory block. So as said, there are a couple strategies, but well, this one is a particularly nice one. And then of course the function returns here the block. And of course when we later take a look into more complex C++ structures, we will see that you pretty much couldn't have modern C++ without a heap memory allocation mechanism, simply because it's extremely useful to be able to have objects which you can pass around, change their ownership, etc. So it gives you a lot of freedom, a lot of possibilities, and as with that come responsibility, it gives you a lot of opportunities to screw something up. But there are ways how this can be mitigated, especially through the use of smart pointers, which is something we will take a look on in one of the later lectures. But now, so first of all, are there any questions with regard to memory management on Windows or in C++ in general? Mm-hmm. Well, if during your testing with the release build you have managed to take all the possible execution paths in your program, then you could make the assumption. But what is quite common with very complicated applications is that a large portion of the code will be only used very rarely. So that only in special cases some other special cases will be triggered, and only then it will do something. And effectively, if you do some normal testing with your debug build, you probably will not hit all these special cases that you added for certain edge cases. And if one of those cases then would have a problem with the with using really already freed memory, then you would not catch this bug. So it helps, but you should not rely on if it works in the debug build, then it will be fine in release build as well. It might in some special cases not be. Okay, any more questions? Okay, so let's go to the next part. So let's save this. Again, I will add verbose commenting to the file and upload it to Moodle, so that it will not be just a wall of code what you will get, but something a bit more intelligible. And now let's create a new project and take a look on how strings are, how you handle strings in C and C++. One thing I think I already mentioned with regard to strings or memory stuff in general is that there is no native type for a string in C or C++. Because like a native, I mean, there is no machine type, there is nothing in the CPU that would directly facilitate the working with textual representation of things with strings in general. But of course you can use all the options that CPU gives you to invent your own string standard, or to use one that someone invented and which just showed. Why is that complaining? Okay, because I didn't sign in, I should do that at some point. But anyhow, so there are, with regard to strings, two things which are mostly characteristic. One is what are you using as a single character in your string. So obviously you would assume that a good choice would be char, since it's called even a character, which can contain 1 byte of some sort. Let's say B for byte. It can also it can contain any printable ASCII character. It can also be really 0, or what would be the biggest one? I mean, you can assign to it null xff, but that doesn't have a printable representation, so that's not a valid character. Oops, but you can let's stick with B for now. This is the most basic type that you use for strings typically, but it's as said very limiting, because you can for the most part only use the Latin alphabet, and as soon as you move to other languages, especially Asian ones, then that is pretty much useless. You can use the Arabic characters, but Arabic numbers, but that's, and the special characters of course, like plus, minus, etc. But text-wise, letter-wise, it's not really helpful. So what people have decided to use to solve this issue are so-called white characters, vchar, t, my vchar, which can contain, which are bigger. So a white char, I mean, it can of course still be just B, but first of all you prepend the single quotes with a L to tell it that it's long character in this case. And if I would have a Asian keyboard, I could print some other more exotic letters, but we can just Google for a smiley Unicode icon and then paste it. Will that work? That should work. Yep, and we have a smiley. So a huge amount of smileys and all the other different symbols you might want to use are available in the Unicode character set. So the Unicode character set is using in fact even more values than can be kept in a vchar. So this is 8-bit, 8-bit, and this is on Windows 16-bit. But for example on Linux, the vchar type is usually 32-bit, which is also well, can be problematic. The Unicode character set is designed to be able to represent pretty much anything in any conceivable human language that was ever used, plus stuffs like emojis and other symbols which might be useful. So arrows, for example, are quite nice in certain situations. In fact, the Latin 1 ASCII extended ASCII character set already contains arrows, vertical and horizontal bars and stuff like that, because those characters have been used on terminals, like in your old DOS box, to draw on the screen things that resemble graphics. So you can use like a symbol that we have it ASCII table. Let's see. We need an extended ASCII table. Can I find it quickly? I think that might be it. Nope. Anyhow, so I don't think I have a good example on that would actually work on Windows. Oh no, maybe this one. Yes, this one's perfect. Graphic copy and So here we have the basic. Well, we have here the basic ASCII character set from the beginning, and then we have here the higher characters which are available, for example, in DOS, and you can use those here to draw things. So you have like a vertical line, you have things which made up. Okay, this two here, it's like an upper edge and the lower edge of a square, so you could create some square thing like a window. In fact, the whole table here is drawn using such characters. So having special characters in your character set is in fact quite a useful thing. Of course, Unicode takes this just to a completely ridiculous amount with the ability to not just represent most of the characters using a 16-bit. So you have 65,000 characters in the simple case, and then in the even more extended Unicode address range, you can go up to 32-bit, almost 32-bit long characters, which of course might appear quite wasteful, but it is in a way quite necessary, because what we expect from a string is to be able to address one character, second, 10th character, to go within the string by index to a certain offset. And if you would be using some more complex encoding scheme for your characters, you could not advance in the string this way. What you, however, can do is you can, when saving on disk, use more efficient encoding schemes. A common encoding scheme, for example, is UTF-8, which basically for a text which is just written using the basic ASCII table will just require 8 bit per character, but if you can also save Unicode characters to it, so it will have a special character that indicates that then it is followed by a certain amount of other characters which need to be put together in a certain way to generate one wide character. Or you can even go as far as having wide characters which then will be made out of two wide characters. So this, for example, the reason why on Linux they chose to go to use VChar of 32-bit, because then you really can put all the Unicode characters in one character in your string, while on Windows, which just chosen 16-bit, in fact there are certain Unicode characters where you need 2 of them to show it properly. Especially with Asian languages, you might run into the situation where you need 2 characters, so not every single character in your string on its own will have a meaning. You will need 2 of them next to each other, and then the routine that renders those characters on the screen will need to print them properly and just print 1 character instead of 2. So this is the first thing about strings, from what they are made up, and for our purposes we will be sticking to char and white char. We will be not looking at other strings, and I don't think we need to look onto the actual encodings like UTF-8 and etc. on disk, because this is something that you can look up if you need it, and I think for most use cases just saving chars or vchars will be just good enough. Okay, and now the second thing about the string, important thing about the string is how do you tell how long a given string is. So with numbers or with normal integers or floating point numbers, the machine types basically, we just define an int is 32 or 64-bit. We have a normal short, which is 16-bit, etc. The length is known, the length is fixed, but a string can have an arbitrary length, and you might even want to add things to a string. So how do you do that? And the solution is that as a string, what we are using normally is just an array of, in this case, in this example, chars, and this array can then be initialized with a string. So let's say test 1 2 3 4. So 1 2 3. So we expect this to be 8 characters, since we put in 8 characters. But if we take a look how big it is, const int test is equals size of, you will see that it actually let me count. Yeah, okay. We expect 8 and it is 9. It is 1 character more than what we typed. How is that? It is that because effectively what this notation gives you, if you make string 2, we can initialize it like an array, and I'm too lazy to type everything down, so I'll just copy and paste from my cheat sheet. Zack. So this assignment is equivalent, it's mostly equivalent to this assignment. It's not exactly equivalent with regard to what happens internally, but it's equivalent enough from a functional standpoint. So we have added the number 0, or the character 0 rather, to our string, and this is how in C and C++ the typical string is defined. It's defined to be terminated by a null character. So the string itself, the content of the string, its payload, so to say, cannot contain a value which is entirely 0. Only the last value in the string is allowed to be 0, and no function which processes strings will normally process a string past the null character. Which of course doesn't mean that the memory area ends there, so we can allocate more memory and put stuff in there. So this is of course not to be confused with how memory allocation works. So for example, you can allocate char Stern Meister 3 malloc 100 char Stern. And now we can fill the string with strcpy string copy, and what it will do it. So this is in principle functionally equivalent to memcopy. Just that memcopy wants us to tell it how long it is. So strlen string 2. Strlen just returns the amount of characters in the string, sorry, +1. We need to also copy the terminating character. And what string lang effectively does, it just goes through the string and counts. So it starts, it sets counter to 1, it checks is this a letter or is it 0? It's not 0, okay, then next index, and it counts up, and when it sees aha, now we got at 0, so let's return the last value of the counter that we had counted up. So in a way it's a bit inefficient, because we are going through the whole string first to get its length, and then we are going through the whole string again to copy it. The obvious expectation is that string copy will be intelligent enough to combine those two operations and be at least slightly more efficient than using memcopy. And of course, if we would want to use vchar, we cannot use vchar with string copy. For those, by str4 is equals okay, malloc 100, and now one catch. Malloc 100 will still only allocate 100 bytes, but if you want 100 characters, we need to multiply this by the size of one character. This way we will still allocate a string which has 100 characters, even though this string in bytes will be twice as big as the string before. And of course, to copy things, you will need to use vcscpy wide string copy, and also wide strings are prefixed with an L, again for long. Test 1 2 3 And what you cannot do, for example, is you cannot copy a wide string to a normal string or vice versa. If you want to, you need to use a conversion function. And of course, there are two things to keep in mind. Of course, you can always copy from a normal ASCII string to a wide string. The value range for the lower characters is the exact same. So you could in fact do something like this: from int I gleich 0 Stichpunkt ist kleiner stren. That's also terribly inefficient because it does string length each time. Okay, let's not be that inefficient. Let's go and cache the value, because it will not change. It will always be the same one. And I++. Okay, and now we can go to our string, address it at I, and assign value which we get from our str2. Okay, let's go to str2. And this will be valid even for the terminating. We need to go +1. Because as said, except a minor exception, every character that is in the lower range of the wide characters is just directly representable by a ASCII character. The other way around, of course, would if your wide string, if your wide string only contains ASCII characters, then it would work, obviously. But as soon as you would, for example, have a smiley or something like that, then it wouldn't. Then it would fail. Then you would get just garbage there. And if you want to do this conversion properly, you would use some conversion function which would effectively convert a Unicode string to a for example, a UTF-8 encoded string. And then you couldn't use the string directly to print it out as a text, but at least you could use it to save it to file and then load it from file. You could, within reasonability, let's say, address characters in the string. You could address the ASCII characters directly, and if you encounter a wider Unicode character in your UTF-8 string, then you would have a few bytes which you need to skip. But it is reasonably useful to use this UTF-8 encoding, especially for saving to files, because it saves you usually a lot of memory, at least, well, mostly half of it, since normally the expectation is that most of your text will be some paths to some folders or some numbers or something that is really nicely represented by the ASCII character. Only rarely you would write some text for something. The most common use case for text is, of course, if you just have a UI where you are displaying things. So there you can write it in whatever language you want, and there are printf functions also for wide characters, so we can actually try printing to screen. So the normal printf takes we used printf earlier. It takes some format string, which we'll take a look on later. But the %s specifier tells it that we want to print a string, and we can use \n for a new line. And if you want to print a wide string, you just use a large S, and then you can feed it the wide string. In this case, it should print two times the same thing. Yes. We have to do it. It's complaining because we have here this smiley. Okay, it's complaining about something else. What did we forget? Okay, yeah, and it's also complaining that using string copy is unsafe, because string copy relies on the... So first of all, it doesn't know how large here your allocated memory is. It might be... it might have been just 1. That would be a problem, but it doesn't know it, so it's unsafe. And also it doesn't really know whether how large this is, so if the 0 would be missing here, it might just keep reading some garbage from some memory area until it reaches some address which is not longer mapped to a physical address. So we actually should not use a string copy. It actually tells you here to use the string copy s instead, Or alternatively, you could add this preprocessor definition, so CRT secure no warnings, to your program to ignore those error warnings, which are here in fact treated as an error. But let's go with the S version since we want to be safe. And as you see here, it actually tells us which options we have. So we have, of course, a source string, we have our destination string, size in bytes, in bytes. So here we need to say we have 100, and now it will copy only up to 100, and if it if our source string would be bigger, it would just abort at this point. So this is one thing to keep in mind. And most of the typical old school string functions in C are considered to be unsafe, so it's discouraged to use them. And therefore we will be trying to use the new ones. We can insert the smiley here in our white string. Yeah, index 4 is fine, so we will replace the... Okay, it didn't print it properly. I'm actually not sure if the Windows terminal can print Unicode in all cases. Printf might not, but we can use white printf. And the thing with white printf is that it kind of inverts the meaning of S and S. So now the small s is, and of course the format string needs now to be white as well. So now the general idea is that a small s means string, and since they wanted later to introduce something to indicate a different type of string, they just went with large S. But at this point, the nomenclature that S is just string of the same type as the format string was already in place. So it's not like small s is a char and large string is vchar. It's just small string is the same as the format, and large s is whatever is the opposite. So that complicates things slightly. And I think I saw at least in some Linux implementations that actually they did it differently, that large S was always Unicode and small s was always char, which is really great if you want to have code portability. Okay, so here it still doesn't print it perfectly, it just prints a question mark. So apparently the console is not good enough for that, but we have this. Do we have the new terminal? No, we don't have. Like, there is this new terminal app from Microsoft, which I think it can support Unicode fully, but well, this is just a Windows 10 VM, and we don't have installed that app, so this doesn't work. But this much about the standard C string. So as you can see, the notation that a null character is like a terminator for your string is not, first of all, not very safe, and secondly of all, not always very user friendly. So other types of strings that you can envision would be strings which would contain an explicit variable, which would contain the length. So an example would be, for example, how the Windows kernel internally handles strings. Typedef talked string. Instead of just using an array of characters, it uses a structure which contains an unsigned short. Oh, no, it's blue. Length, and another unsigned short max length, and then it contains a char or a white char, which contains the actual string. So now, and of course we want this to be a string or a asterisk string. That should be all capital letters. And they usually call it a Unicode string, actually, or ANSI string. So with char it would be ANSI string, and with vchar it would be a Unicode string. And the idea here is that instead of relying on looking in the string where it ends, you can just check the variable and you already know it. And the next nice thing is that you have a max length, which kind of resolves the security issue here, because if you would want to copy to a string of this type, you just check is the maximum length well, large enough or not, and then return an error if it's not. So this type of string is preferable wherever you can use it. Its downside is that it's not just one single pointer, but just a whole structure. So as we have seen before with the function calls, when we are just passing a pointer to an array, for example, then we can just pass it through a register or with using one position on the stack. But if we are passing a structure by value, then the thing will make a copy, allocate additional memory, so it will be much more computationally expensive to pass this kind of string in comparison to just passing a simple pointer. What we of course can do in most cases is that we will be passing a pointer to such a string instead, which is quite reasonable to do in most cases, because it also allows you to return value. So for example, a string copy function which uses a string like this would be able to check the length, check the max length of course, but then would be able to modify the length of the new string. So an example would be, for example, we will create two strings. X2. We can actually initialize it like this. So length is 0, size will be, let's say, 100, but we don't fill it in yet the buffer, and then we use here x1 punct buffer is equals malloc punct max length, and here for string 2 we do the same. And this way we have only one place where we specify the size, so if we change the size later on, it will automatically affect all our subsequent uses of it, and it will maintain security. So it will now have a function copy x. Okay, let's first fill the string. Let's maybe make first a function fill strings, which takes a, we need to move this up first. Fill, yeah, reference x, comma, and here we will have a normal string 3, 4, because somehow we need to fill it. The downside, unfortunately, is that this way of typing strings using null terminated strings is how C was designed initially, and this is only how you pass all the strings. So you will always have some C strings in your program, but you can try to move them to better implementations of string as soon as you can. Let's say boolean, because it might also fail. Pointer to a string, strings, and here's stern star, strings and star. And what we do is first int len, we should use size of sorry, int len is going, so instead of star len, and then we check if len, we need +1, if len is less than, well, actually not, we don't need to keep the null terminating character. So the thing with Unicode strings is you don't necessarily need to add this null terminating character, although usually it would be a good idea to do so, because if you have a function which just takes a normal C string and your beta string has the null terminating character, then you can always just take the pointer and pass it without having to make a copy. So let's assume that we will want to do the same thing. So we check whether it will fit. So if it will not fit, then return false. And if it will fit, then we can mem copy. Right, strings buffer comma string comma len, and of course strings length is equals okay, that's not actually what we want. We would either write len -1 or change the code to have the +1 somewhere else, because the length as such we want to be without the terminating character. And then of course we could make a function to make a copy. So let's say ball copy string, which will take 2 strings, 1 and 2, and this one is like this and the one is const. So the other one will not be changeable, or let's call it destination and source. And it will be the first homework from today's lecture to implement this function. I think it's quite simple, so it should not be difficult. Right, here this needs to be const as well. Okay, and now what we should take a look on is more about printf, and maybe at least mention some of the typically useful functions. So as here you already saw, we have a string copy, but what we also, for example, could do is if you want to add something to a string. So strcut, but it will also complain that it's not safe. So let's go with strcut s, the first string. We then specify the size in bytes again. Then we can attach something, for example, like this. So strcut will, why is it complaining? Does it want? So destination, size in bytes, const char source, that should be fine. Char in bytes. Let's see if that compiles. No, it doesn't. String free is a character. Yeah. Char s const char. That's not the white string. No, it's fine. Yeah. So what it does, it goes to the end toward. So it starts at the beginning. It goes to the null terminating character. Then it adds your string, copies it including the terminating character, and then we're done. The string was modified. And since it's a safe function, it will check whether the length is long enough. So one thing you probably already see here is that the string length is limited. So even using such a string as used by the Windows kernel, you need to decide what's the longest string you want to be able to put in here and stick to it. Of course, you could go with a function that would reallocate the memory, but that makes things complicated. So usually if you would want to work with strings, you would try to use a C++, not just plain C, because in C++ with classes you have objects, so you can define a class of type string, or you can actually use one that's provided by the STL framework, like std string. Or if you're using Qt framework, you have QString, and Microsoft had some C string in the MFC framework long time ago. So there are many implementation of complex C objects which represent strings, and the nice things about them is that you can append, truncate, cut things from the middle, search of index, and do all those operations, and you don't have to care about how large the string really is, because the object will do all the operations internally. It will take care automatically of reallocating a larger memory block if needed. It will take care of deallocating memory if only a very small fraction of the string is used, etc. So we will be revisiting strings at some point once we start the C++ part of the lecture, which will be soon. And I think the last thing to say here about strings will be more about this printf function. So printf, as we used it, not just prints to the console, but what you can also do, you can use sprintf, which then prints to another string. So you can use sprintf let's take our string number 3, then we provide some format, test blah loop %i, comma 1 2 3, and that's now another format specifier. So as we already saw, it's a string, I is an integer, and in fact there is a whole bunch of other optional string identifiers. The list is not exhaustive, so you might experience more. I mean, % like just 1%, it's just a way to allow you to write a % in your string specifier, but I is your typical integer to base 10. You can use octal, you can have of course strings we mentioned, you can use base 16, you can use base 16 uppercase, although often large X will do the same thing, and the format specifiers can also be used in a more complex way. So for example, if we have here %08 large X, comma 0x a b b c c d. So you can specify in this case how long your number should always be, and with which should the number be padded from the beginning. So in this case, okay, this is a stupid example. Sorry about that. Let's go with something like this. So when we run this code now, we will end up with a number that looks pretty much like this, except it will be missing the 0x at the beginning. This of course also unsafe. 100. Yeah. And then if you look inside, it created the number as we wanted it, with zeros. If you would just use %x, it would not add any leading zeros to it. It would just be ccdd in this case. And of course, if you want something to look exactly like a normal hex representation, you just add null x before that, and then it will provide you the representation you want. What else you have? You have f for floating point numbers, which is also quite nice. You can select between floating point x and exponential notation. If you use e, it will be the exponential notation. And a typical thing which you would use with points would be a typical thing you would use with floats would be %.2f, which means that you want 2 comma place 1 2 3 4 5 6 7 8 9. And now if you run it, you will see that it will just print 2 commas and space, and the rest will be removed. So you see it just took 5 and 7 and it ignored sorry, it took 5 and 6 and ignored 7 8 9. If you would just have f, then it would just print the whole thing. And given that floating point numbers can have a lot of rounding, so now it looks like this. So let's say 1 divided to 3, that will give us a lot of 3's in our string. So you might not want something to look this way, and then you just specify how many commas you care. For example, if you print file size, you should just go with 2 commas, maybe 3 commas, but everything going past that is just not necessary. So that's why you have this formatting ability here. And there is quite some more ways how you could format strings or numbers or stuff that you print within strings. I will add some verbose list, also much more other functions that you can use with strings as well, so that you can review them and use them if you want. But the list will only contain the unsafe versions, so you need to check which safe versions they are, which would be corresponding. Another thing which we already used with regard to strings, but in fact have not necessarily addressed fully, are escape sequences. So when writing code, you are still limited mostly to using a normal ASCII characters. Of course, as we have seen, you can put Unicode into your modern files nowadays, but that was not always like this. So and of course you might for some reason want your file to be just entirely ASCII and not Unicode. So what you can use are these escape sequences. It's called as an escape sequence because it uses an escape character, which is defined as the \. and it allows you, for example, how would you make a what is the quotation mark inside quotation marks? As soon as the string parser sees a quotation mark, it says string's done, and it complains, it returns an error. But what you can do is you can escape the character. So by using the escape character and preceding the other character, you are telling the parser, which is reading the code and generating the binary representation, whatever follows next, it's special treated the appropriate way. So in this case, it just takes the quotation mark and it allows you to make a string which contains a quotation mark. What you can also do is, for example, \n or \r, which, as said here, \n is line feed, so it moves to the next line, and carriage return moves. So line feed is like moving up and down, and carriage return is moving to the beginning of the line. On Windows, it's typical to use always \r \n, \n, and in fact, up to some build of Windows 10, the normal Windows Notepad even did not properly show files which only used the \n instead of \r \n. But on Linux, for example, it's customary to just use \n, and it will have the meaning of both carriage return and line feed. Generally, the whole meaning of carriage return is very much about mechanical printers, where you have one motor that moves the line, zack, 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 and one that moves the carriage then back to the beginning. So with modern computers, this is pretty much meaningless, but in fact it can be useful, because if you have a console window, I don't know, like this one or something, and then you would want to overwrite something on the console. You could of course use special commands to move the cursor to some offset and then write something there. But one of these special commands, and the simple one, is just the \r, because it moves you to the beginning of the line, and then you can start again printing characters, and they will be overwriting the characters which already are there. So if you have one line which says 10%, please wait, then you can overwrite the line with one saying 20%, please wait. One thing to keep in mind is that if whatever you are overwriting the line is shorter than what was in this line before, the other characters in the line will still stay there. So ideally you would then pad your status line with spaces at the end, so that it always overwrites all 80 columns of your typical terminal length. So it can be useful. \t is just a tab, zack, like this one, which might be helpful with formatting. Vertical tab I never use. \0 is just a placeholder for the actual 0. You can also use here a \% to print the % sign, but you could also use %% to print the percentage sign, so this is quite flexible. And then we have these here, which allow you to really print, to pretty much put anything into your string that you want to put in. So the most common would be this one, where you can just in hex write some character value. So I don't remember what this was, but let's see what it will evaluate to. It's probably some smiley or something. So using the U, you can specify enough characters to have some. It will not work because that's not Unicode. So for this test we need another test case. SV. What was that for this? What was the printf for SV? I think it was, yeah, it's SV printf, and then the S version should be the safe one, yes. And we need string number 4, and this needs to be wide. But now we can actually put a Unicode character into the string without having our whole file to be Unicode. So if we run this, you will see what I guess it was a smiley. What was it? It was a smiley, yes. So by the way, now you see how the smiley is represented in Unicode, in 32-bit Unicode. Don't know, it's not 32-bit. Sorry, it still fits into the 16-bit range, because like that's our no, it's 2 characters. So apparently the smiley already would not fit into a normal varchar. So if we put a try to step through our varchar step by step. So 0 will be T, L, S, T. Then we have space. Sorry. 4 is space, and 5 is just an unprintable character because it's just a part of the smiley. 6 will be the other half of the smiley, which again is not in this way printable since Windows opted to use 16-bit white characters and not like Linux the 32-bit white ones. But if we proceed with stepping through the string, we get again a space and again intelligible stuff and no sorry, this was wrong, and no gibberish. Okay, so here we have our terminating null. Of course, in Unicode the terminating null are 2 null bytes in a row, since normally just a yeah, as you see here, the normal in normal white card representation, sorry, white string, white char. I'm sometimes saying white card, which is completely wrong. I mean white char, of course. Usually the first byte is always 0, as long as you have ASCII characters. That is, of course, with here the use case, the case of our smiley. As you see, the first characters were something different. Okay, so this much to this. Yeah. This much to this. Anything else we should say about strings? Probably not. Are there any questions about strings? No questions? Okay, so if there are no more questions, then let's see what we should take a look at next. Usually I would now start with a self-made container object, but since we only have half an hour, that kind of is a bit too much just to start and leave you without continuation. I don't want to leave you on a cliffhanger, so to say. So let me quickly see what would be small enough that we could fit it in whatever time we have left. Maybe file IO. That would be something that is small enough and it fits well with strings. So let's just take a look on that. Yeah, I think that would be a good idea. So let's create a new project. So this one I will minimize. Create project, next, just call it IO. So it will be just called IO, and it will be a bit broader than just file IO, but we can start with file IO, and that will not be too much of a cliffhanger if this is all we do. And it gives us opportunities for some more homework. I mean, if you want more homework, we can of course make some more homework about strings, like make a function to not just copy a string but to concatenate two strings. Maybe that's a good idea. I know people don't like homework voluntarily, but I think this is good to learn things. Test and source. So the append string is supposed, I will write this more verbose. So here this one, don't forget to check size, max, how do I call it? Max size, max length. max. Yeah, so that is still pretty simple. We could also have make a function that makes all the characters void to lower. Make all characters in string lowercase, and of course to upper will make them uppercase. Make all in string uppercase, that's easy enough. And let's add one funny thing. We will be using also an unsigned short. This will be the optional one. Find substring und to find to optional to find the substring in the store and return it starting offset. When string is not found, return -1. That might be a bit more of an advanced optional assignment, but it's not too difficult based on what we have already done, I think, because here you see how you can go for a string and it's really just matching characters and then returning the offset if something was found. So I think as an optional one this is fine. And then let's go to our standard IO. So let's include some headers. Oops. lib. And this is a very generic way of accessing files, and it would work on pretty much any platform. It's an extremely old school way, so on Windows, if you would want to be more modern, you would use other APIs, but then it's only Windows compatible. So if you want to write something that would work on Windows and on Linux, then using this very old stdio functions is the easiest way to do. So first of all, we need a way to refer to a file, which we first will open. So it's here called a file handle. Let's call it demo, and now let's open a file. So like f open stands just for file open, and then we can provide it a file name. So let's say demo file takes them, and then we need to tell it what we want to do with it, and we use W to tell it that we want to write to it. And if we don't provide a full path, the file will be just created in whatever directory is the current working directory of our application. The concept of working directory is something from the DOS era, but it's also on Linux or on any other operating system that had at least at some point some sort of console interface. So it's pretty much in any operating system you will encounter that you have the concept of the current working directory. You can change this using various API calls, but I'm not sure if there are any that would be platform independent. And normally if you just write a program, then you would start it from some directory, so you might not necessarily need to change the working directory. So one thing now we do is we check, of course, if it works, so if the file was open. If it's null, then it wasn't. We just return. And there is a couple of operations which we can do just write, except so in addition to writing. We could of course do reading. We might want to write to a file but not overwrite what's in the file, but just want to append to the end, so that would be A. We might want to be able to read and write. We might want to be able to read or append, so there are quite a few of these options that you can specify for the fopen function call. And the way this works internally is that the operating system will open the file for you and give you a handle to a file. So this is a value which meaning in the context of the operating system is to represent which file is currently open and keep some associated state with the file. Normally when you are working with files, you need the ability to specify from where in the file you want to read, or to which part of the file you want to write something. Since files can be much bigger than what will fit in your memory, it is not a typical use case for most files to map them somehow, or to just read the whole content at once to a buffer. But usually you would just read them piece by piece, portion by portion, and this means that the operating system has to maintain some internal state to the least, of course, where you are currently right now with writing to the file. And in practice, there are of course much more information. It will need to track how large the file is. It will need to track which sectors on the disk the file occupies. But these are details which for you are not relevant. For you, it's the only things that are relevant is the ability to read, write, and to change the current position at which you will be reading and or writing. So doing this, you can with the fseek command, function, to which you specify again the file handle. Then you specify where you want to go. So let's say we want to stay at 0, and then you can specify the origin. So the origin, there you have the ability to specify either from the current position. So if you want to just advance from wherever you are right now, or you can specify set, which just means that you are specifying the absolute offset within the file. And you can of course specify also end, in which case you would be specifying an offset from the end of the file. So if you, for example, would have a format like many, maybe not most, but many archive files like zip, rar, etc. are, they are made such that the actual header is at the very end of the file, because it needs to be kept up to date and changed while it's adding more and more files. More and more files to the sorry about that. Okay, sorry about that. Where was I? Yeah. So when they are creating the typical archives, they will be changing the data which they would want to put in the header, so they just cache them, and when they are done adding all the files, they just write the header at the end. So there are various use cases where you would want to have a file format in which you would start reading the file from the end. So this is why you have the seek end option when specifying an offset. And then of course we want to read something, so it's simple f. Now first we want to write something, so we write using fprintf, which for which you don't need a save version, because the file is always as big as you need it, or you could just get a exception that your hard disk is full. That can happen. It's known to happen to some people, to have a full hard disk. And then you can just use the normal formatting sort of format, where you just can print, like with printf, just that whatever you do is you print it to a file. What you can also do, of course, is if you don't want a formatting but you want to write some binary data, you can use fwrite, which takes a buffer. So let's take a buffer which just contains a string. Then we specify the size of one element, which is in this case a character. Then we specify the amount of elements, which are 4. And then we specify the handle again, and then we can rinse and repeat as long as we want until we wrote everything we wanted to, or the hard disk ran out of space. And then once we are done with that, we can close the file using fclose. And it's a good practice to to then set it to null such that we don't such that we are not tempted to reuse the handle for something else once it's not longer working anymore. Any questions at this point? Okay, no questions? Then let's run our program and check whether it created a file with the content test1234. Or maybe there is a mistake somewhere. Why would that want us to specify? Okay, yes. They changed it because too many people were not checking the return value of demo. So now this will return you an error or success, and only on success update the demo. But well, let's run it again. Okay, the function ran, so let's see if it created the file. Probably inside here. Yep, it created a demo file with our test1234. And what we can now do is pretty much the opposite. We can read the file. Oops. We can copy something from here. We can copy this. We can copy also close. It's always useful to copy as much as we can, because then we save on time on typing things. But we want here the R parameter since we are reading. And now it's up to us to decide how we want to read the file. So one way we could read it is, of course, we could just read everything to a buffer, but as I mentioned, for particularly big files that might not necessarily be the best thing to do. We could try to use fscanf, which is like, it's like the opposite to fprintf. So you have specify a format. So this was in this case test space %d, comma reference int x, and what it will do, it will expect to find test, then it will read this part. So we can in fact this way already extract some this is not safe. Why? What does it want? Okay, file stream. It takes the same format, it's just a safer version apparently. And here, okay, we need to turn off hex. Suck, it read the 1234 from the file. One could of course also just try to read a string, and I think this is where scanfs will be particularly useful. Just %s, then we need here char star 100, and I guess I need to refer to the manual of fscanf, because it will need to somehow be told how much it can put into the string, and since there can be many strings, it will not be part of the typical format. Yeah, so you are supposed to provide 2 arguments providing the length as an additional parameter. So the normal so the normal fscanf would not take the 100 here, it would just read the string. And one thing that is problematic a bit with this thing, I don't think this is particularly smart with reading, so it just, okay, so it's making gaps at spaces. So actually it's not that bad. We can also read %d at the same time, but this means we cannot read a space in. So if we have a string with a space, we need to know where the space is. We cannot just read it in one go, which kind of makes sense, because otherwise as soon as we want to read a string, it would just ring until the end of the file. So this is another way, and of course we could just use fread. We should probably use the S version, otherwise it will complain as well. But of course then we don't want to do this. Go with the string, then we specify buffer size 100, then we specify element size 1 and element count. We don't know as many as they are. The string has, how much does it has? Test. There's 9, I think, elements. And then, sorry, buffer was first. So first and then the buffer. So this should read the whole string to a string. And, well, there is no terminating null, so the rest is garbage, but it worked as well. And what we could do is int ftel, I think was. So int size is like f. I think ftel tells us the size of the file, if I remember that correctly. So let's try. And then if this works correctly, we also want to manually add the terminating 0. Let's run it. And okay, ftel didn't do what I thought it does. Let's see. Maybe ftel tells us the position at the. It probably tells us the position. It doesn't tell us the size. That is probably. Yep, it tells us that's really not cool. But we can work around it. We can say go to the end, seek end. Then seek so then tell us where the end is, and then go back to the beginning. Yeah, it's a very old API, so it's not necessarily good. But now it worked. We have test 1, 2, 3, 4, and of course, ideally, you would want to first save the old value. Oops. Alt pos. Then seek to the end, get the size, and then seek back to the old position, so that you don't change anything in the state of the file. More modern APIs, as said, will not have such issues. They will just give you the current position, they will give you the file size, they will give you many other informations. But as said, those are not. So those are either non-standard or not platform independent. So if you are using Windows APIs, then it only works on Windows, and if you are using something like the QFile object from Qt, then you need the whole Qt framework to use it. So then it's not longer standardized. Yeah. Any questions at this point? We are running out of time. We have 8 minutes left, so we will finish now, unless there are any questions. During the next lecture, we will take a bit more looks into I/O. We might try some Windows-specific things like mapping a file to a memory region and then just reading and writing from it. So that might be fun. It will only work on Windows, of course. So that's a limitation to keep in mind. Yeah. Good. So, are there any questions? No questions? Okay, if there are no questions, then we are done for today. I will upload all the 3 projects to the Moodle. I will upload the homework, which I don't think is too complicated. If it is, then let me know during the next lecture, then we will maybe take a look on that. And the most time of the next lecture will be spending creating our first useful program that does something and that implements using just C a container object. And after that, I think we will move on already to C++. Well, there is one more thing we should do, which are exceptions, which we might also take a look on during the next lecture. But but since there is a lot of exception handling in C++, it would also be fine to do all the exception stuff in one go. Okay, so if there are no questions, then see you next week and have a nice weekend. Bye bye.